Has Sherbrooke reopened its campus?
Not yet. Well, in a sense, yes, but the classes are not fully back yet. So in the fall, it will be some kind of hybrid version, online and in presence. Yeah.
Okay, so
But
for instance,
indeed,
lab classes in person.
Yeah, the university is not closed. Yeah, there are actually people working there at this point, but personally, I have been working from home for months now. So yeah, and some of my colleagues are likewise, but experimentalists are gradually returning to work. Yeah. How about there?
Caltech has been completely shut down. Well, actually, no. I think they're starting to allow some experimental groups to go back on campus. But again, for me, it's been completely work from home for a few months.
Yeah.
And then I'm calling in from Alaska. We ended up escaping to Alaska where the numbers are much lower, and we're working from here for a few weeks.
I see. Interesting. Yeah. So you're which city of Alaska is Anchorage?
Anchorage, yeah.
Yeah.
So it's unusual for me where I'm looking outside and it's pouring rain, and I think I've only had a couple days of rain the entire time since moving to California.
Yes.
Refreshing.
Yes. Okay, so maybe we'll get started. So hi everyone, and thank you for coming. And it's my pleasure to introduce today's seminar speaker, Christina Knapp. So some of you may have met her already. She visited Sherbrooke in the past. So Christina did her PhD at the University of California, Santa Barbara, where she worked with Chetan Nayak. And her thesis subject was topological quantum computing with Majorana zero modes. Then after that PhD, she obtained about a year ago, and then she joined Caltech as a postdoctoral fellow in the groups of Jason Alicea and Gil Rafael, where she's continuing to do some work on Majorana zero modes and other things. And soon, in the near future, she'll be going back to Santa Barbara as a staff member at the Microsoft Station Q. So we are very pleased to have her again with us today. So so the floor is yours, Christina.
Wonderful. Thank you all for tuning in. And today I'm going to be talking about a recent work looking at time-reversal-invariant topological superconductors and the fractional Josephson effect. And this is work that was done in collaboration with Aaron Chu, who just got his PhD from Caltech and will be a postdoc at Princeton in the fall, and Jason Alicea. And here's the archive posting for the paper. So before we dive into the meat of the talk, which will be looking at the fractional Josephson effect for time-reversal-invariant topological superconductors, I first would like to spend some time just reviewing topological superconductors. And as Jan said, I have done a lot of work looking at Majorana zero modes, and so I'd like to spend some time communicating what a Majorana zero mode is and why you should care about it, whether you're coming from a condensed matter or a quantum information background. Next, we'll look at what happens if you add time reversal symmetry to a topological superconductor. And this creates a time reversal invariant topological superconductor, which is a mouthful, so we abbreviate it to TRITOPS, similar to Triceratops. I believe the person who came up with this acronym had a little kid who liked dinosaurs at the time. And so we'll look in particular about what is different about a TRITOPS wire compared to a standard Majorana nanowire. And then lastly, the big focus of the talk will be looking at whether there exists a fractional Josephson effect for a TRITOPS junction. So we'll go into why this question is a little subtle, and then we'll look at what the answer is to this question. So first, beginning with topological superconductors in Majorana zero modes, there's some mystery surrounding Majorana zero modes and Majorana fermions, and this is because it means different things in different communities. So originally, a Majorana fermion showed up in high energy physics because Ettore Majorana realized you could factor the Dirac equation into two real wave equations, and he proposed that the solution of these real wave equations would be a new fundamental particle, a new fundamental fermion that is called the Majorana fermion. And in particular, this would have the strange property that it would be its own antiparticle. And the reason for this is because it's a solution of a real wave equation as opposed to a complex wave equation. So if we switch from wave equation language to thinking about operators, this first bullet point essentially means that I can rewrite a Dirac operator, like an operator for an electron, in terms of two Majorana operators, which I'll denote by gamma I and gamma j. And you could think of these operators as corresponding to the real and imaginary parts of your Dirac operator. And then the fact that this should describe a fundamental fermion that it's its own antiparticle means that these Majorana operators have to be Hermitian. And then furthermore, they're fermionic, so they should anti-commute with each other. And these two equations end up implying the standard Dirac fermion anti-commutation relations. So this is what we mean in high energy physics. In condensed matter physics, when we're looking for something Majorana-like, rather than looking for a fundamental fermion, we're looking for an emergent excitation that's described by a Majorana operator. And it turns out that superconductivity is a natural place to look for this. And that's because in superconductivity, your quasi-particle operators are superpositions of electrons in holes. So for instance, in a standard S-wave superconductor like aluminum, you would have a superposition of a spin-up electron and a spin-down hole. And this is starting to look like it might be able to satisfy this Hermitian property of a Majorana operator. However, because in S-wave superconductors, you have these spin labels attached, you'll never actually be able to satisfy gamma equal to gamma dagger, which means that we have to go a little beyond S-wave superconductivity, for instance, to look at P-wave superconductors. And in this case, we can end up dropping the spin label, and we get to have something that looks more similar to something that might be Hermitian, except for there's some constraints on these U and V amplitudes for the electron in the hole. So in fact, what we need to consider is that a superconductor has particle-hole symmetry, meaning a quasi-particle operator at energy E will always be equal to a quasi-hole operator at energy minus E. So in order to have D equal to D dagger, we're forced to look at zero energy. And that's why we're looking for zero energy modes described by Majorana operators, and this is why we call them Majorana zero modes in condensed matter. So a superconductor has a superconducting gap, meaning normally you don't have any subgap states. And so if we're looking for a zero energy mode, it makes sense to look for topological defects where your superconducting gap closes and then reopens. So right at the boundary between where it closes and reopens, you might expect there to be a zero energy mode. So in a 2D superconductor, this means if you're looking for Majorana zero modes, you're either looking at a chiral edge mode of the system, or you're looking to a bound state to a vortex core. In this talk, we'll actually be focusing mostly on 1D topological superconductors, where topological defects correspond to either endpoint of the superconductor. So now we'll have two Majorana zero modes, gamma 1 and gamma 2, bound to either end. And in particular, these are going to be these emergent excitations described by Majorana operators. And so far, you don't have any real reason to know that they should be interesting. We'll get into that a little later. So it's helpful before we go on to give an example, a simple example of how you can actually have these spatially separated Majorana zero modes appearing. And this is a toy model called the Kitaev chain. So this is a very simple model of a spinless superconductor where we just take a chain of electrons, which I'm representing by these pale blue dots, and then we have three terms in our Hamiltonian. We allow hopping between adjacent electron sites. We have some chemical potential term, which says whether it's energetically preferable to occupy a given site or not. And then additionally, you have some superconducting pairing between adjacent sites. So this is just some toy model of a spinless superconductor. And then we can use the fact that any of these electron operators can be rewritten in terms of a pair of Majorana operators to rewrite this Hamiltonian in this way. So it's the same Hamiltonian as before, we're just now thinking about it in terms of each of these electrons corresponding to two Majorana operators. And in particular, what you'll notice is that if I take the limit where mu is much greater than the terms that couple adjacent sites, then I have a trivial phase where I've paired each Majorana operator belonging to the same site with its partner on the same site. And in this case, we have a unique ground state. We call it the trivial phase. It's just an atomic insulator where we either want to occupy every site or not occupy any site, depending on the sign of mu. However, we could take the opposite limit where mu is small and instead delta plus t is the dominant term. And in this case, we strongly pair Majorana operators belonging to adjacent sites. And what you see is that there are two Majorana operators that essentially don't appear in the Hamiltonian, corresponding to either endpoint. And these will commute with the Hamiltonian because of our Majorana anti-commutation relations, which means that we'll have zero energy modes. So these at either end will correspond to our Majorana zero modes. And now the interesting thing about this phase, where you have a pair of spatially separated Majorana zero modes, is we could do the same trick as before, where we rewrite this pair of Majorana zero modes in terms of a single electron operator, but now it'll be a non-local electron operator, and it costs zero energy to occupy or not occupy that site. So we say this topological phase has a degenerate ground state with different fermion parity. Okay, so this is the essential idea of a Majorana zero mode in a simple model where it could show up. Now you might ask, why should I actually care about these Majorana zero modes? From a condensed matter standpoint, a reason to care about them is because they are examples of non-abelian topological physics. So what that means is that they have something called fusion and something called braiding. Fusion is really just asking what the joint state of a pair of Majorana zero modes is. So if I look at the joint state of gamma 1 and gamma 2, what do I get? What we're seeing is that I can define this non-local electron in terms of gamma 1 and gamma 2, which here I'm calling C12. And then I can look at the number operator for this non-local electron and ask whether it's occupied or not. And this corresponds to the joint state of gamma 1 and gamma 2. And because it costs zero energy to occupy or not, this is telling me I have some ground state degeneracy, and that this pair of Majorana zero modes fuses either to the trivial state, an unoccupied fermion or a boson, or it fuses to the occupied state corresponding to a fermion. So non-abelian fusion in the case of Majorana zero modes just refers to if I have a pair of Majorana zero modes, their joint state can either be a fermion or a boson. Braiding asks what happens if I adiabatically exchange a pair of Majorana zero modes. So recall when we're used to thinking about fundamental particles, everything's either a boson or a fermion. So if I adiabatically exchange a pair of fermions, my wave function just picks up a minus sign. If I adiabatically exchange a pair of bosons, I just pick up a plus sign. And this is only really a natural question to ask if I'm thinking about identical particles. It turns out that the story is a bit richer if you're focused on two dimensions and you're thinking about emergent excitations. Now exchanging a pair of quasi-particles can actually pick up some other phase or even change the state of the system. And that's what's happening with Majorana zero modes. If I start off in a state where I have gamma 1 and gamma 2, and gamma 3 and gamma 4, and then I adiabatically exchange gamma 2 and gamma 3, then I could imagine that this non-local electron defined by gamma 1 and gamma 2 is initially unoccupied. The non-local electron defined by gamma 3 and gamma 4 is initially unoccupied. So that's what I'm writing down here. And then let's imagine this y-axis is time, and I exchange gamma 2 and gamma 3. It turns out that this can actually rotate the state into a superposition of states where either both of these non-local electrons are occupied or both are occupied. The important thing to notice, okay, so what we're seeing here is that adiabatically exchanging our Majorana zero modes can do more than just pick up a plus or minus sign to the state. It can actually rotate the state within the degenerate ground state subspace. And that's what's meant by non-abelian braiding. So in particular, it's important that you have some ground state degeneracy, and then that exchanging your Majorana zero modes can actually implement a rotation within that ground state subspace. An important thing to notice here is that this rotation is quantized, meaning that the phase I get under doing this braid is fixed to be I. It's not just some non-universal phase showing up between 0, 0 and 1, 1. And in particular, the only thing that matters here is that I'm staying in the ground state subspace, so I'm doing an adiabatic exchange. And then also which pairs of Majorana zero modes I exchange and whether I circle any other Majorana zero modes or not. And so this is going to be important later when we're drawing contrast to the case of TRITOPS. Now, the other reason you might care about Majorana zero modes if you're a condensed matter physicist is because not only should they display this non-abelian topological physics, which is very different from how fundamental particles act, but actually we have a chance of realizing experiments that demonstrate Majorana zero modes. So this is not something that I'm going to spend much time on, but there's been a lot of progress that's looking at how you can realize a topological superconducting wire by combining a semiconducting wire, in this case indium antimonide, with a superconducting shell, in this case aluminum. So this is a schematic of a picture of a transport experiment where they're essentially looking for a zero energy state, and they're using this as evidence of a Majorana zero mode appearing. I just want to emphasize that there have been a lot of experiments on this type of system or very similar types of systems that have different degrees of evidence of Majorana zero modes. And so this is one reason that condensed matter has really focused on Majorana zero modes as opposed to other type of non-abelian topological physics, is because we think we actually have a chance to probe this interesting physics through real experiments. Now, suppose you're not coming from a condensed matter background, but rather you're a quantum information scientist, or your main goal is to build a quantum computer. You should also care about Majorana zero modes because they could be a building block for topologically protected qubits. That is, these Majorana zero modes encode some ground state degeneracy, and that could be used to encode your qubit state. And the reason that's beneficial is that you're storing your qubits non-locally in such a way that they will be protected from local noise sources. So it doesn't matter if I have some fluctuations in the vicinity of gamma 2, it won't change the state of psi. Instead, I would need some fluctuations or some noise that actually connects gamma 2 to one of the other Majorana operators here. So in particular, to have a topologically protected qubit, I need to have some ground state degeneracy, and this degeneracy needs to be exact. And in particular, we usually require it to be exponentially, any changes in this ground state degeneracy, any ground state degeneracy splitting, to be exponentially suppressed in macroscopic parameter ratios of the system. So one way of kind of a schematic way to think about this is you could think of a normal qubit, a conventional qubit, as being stored at some point on the surface of the Bloch sphere. And then any local noise can come in and slightly change the position of that point. And that would correspond to some qubit error. And the motivation behind using a topologically protected qubit is instead you're encoding your qubit state in something non-local, something global, like the number of times you circle a cycle of the torus. And then even if you have local noise coming in and slightly perturbing that state, it doesn't change this non-local winding number. To have an error affecting the topological qubit, you would have to have a much more drastic noise source, for instance, that cuts open the torus and slightly rotates it and glues it back together. Now, the other main component of using topological qubits for quantum computing is that you can do more than just store the information in a protected way. You could also manipulate the information non-locally via braiding. So we saw before an example of how braiding a pair of Majorana zero modes can implement a gate that has a quantized phase difference between the states. And when you do this, you're keeping your Majorana zero modes separated at all times, so you're never opening them up to local sources of noise. So these are the two reasons really that people have focused a lot on Majorana zero modes and that there's been a lot of interest in these systems. Yeah, I just want to emphasize that in order for braiding to be useful, it relies on there being a quantized braiding phase. Okay, so what is a Majorana zero mode and why should we care? A Majorana zero mode is a zero energy excitation, for instance, of a superconductor that's described by a Hermitian operator, but it has fermionic anti-commutation. And it displays non-abelian fusion and braiding and could be a building block for topologically protected qubits. So now we'd like to add time reversal symmetry to the problem and look at what happens to a topological superconductor if it becomes time reversal invariant. In particular, we want to look at the differences between this new system and a Majorana nanowire. But perhaps before we move on to this new section, if you have any questions about topological superconductors or Majorana zero modes, this is a great point to pause and to ask those questions. And I'll use this as an excuse to get a drink of water. Okay, and I should say feel free at any point to interrupt if questions come up. So moving on to TRITOPS wires. First, it's useful to remember what time reversal symmetry is. So this is an anti-unitary symmetry that essentially takes time to minus time. And if you have fermions, there's a two-dimensional representation of this symmetry that squares to -1, and this is what we'll focus on today. And essentially what that means is if you have fermions, you can attach some spin label to them, and under time reversal, they have to transform into a partner fermion. So C up would transform to C down, and C down would transform to -C up. And you can see that if I apply this twice, I'll get C up goes to -C up, C down goes to -C down. So we call these Kramer's pairs. And if we think about the implication of having time reversal symmetry and Kramer's pairs on the Kitaev chain, it means that every electron in this chain now needs to have a Kramer's partner. So in order to have a time reversal invariant topological superconductor, we essentially need two copies of our standard topological superconductor that are related to each other by time reversal symmetry. So in particular, a single topological superconductor has a Majorana zero mode at either endpoint. A TRITOPS wire will have a pair of Majorana zero modes at either endpoint, and we call this a Majorana-Kramer's pair. The two Majorana zero modes are related. They transform into each other under time reversal symmetry. Normally, if I have a pair of Majorana zero modes that are in the same spatial location, I'd expect generically that they'll hybridize with each other and split their ground state degeneracy. But in this case, they're not allowed to because of time reversal symmetry. If I look at I gamma j up, gamma j down, and I apply this type of transformation where Sj is just a plus or minus sign, then under time reversal symmetry, this joint state of the Majorana zero modes will transform to the minus of itself. This means that we're not allowed to have any of these in a time reversal symmetric Hamiltonian. So it's worthwhile to look at the two properties of a standard topological superconductor that makes it interesting, fusion and braiding, and ask what happens in a TRITOPS wire. If we first think about fusion, and really we're thinking about the ground state degeneracy here, we see that time reversal symmetry prevents the Majorana-Kramer's pair at a given end of the wire from hybridizing with each other. And then the standard topology prevents the Majorana zero modes at different ends of the wire from hybridizing with each other. So we have a mix of symmetry and topological protection that leads to two degenerate ground states of the same overall fermion parity, or equivalently of 4 degenerate ground states in total. So we've essentially doubled our ground state degeneracy by adding time reversal symmetry. If instead we ask what happens with braiding, and here I'm just reminding you that for a topological superconductor, the braid operator can be written in this way, then you might think, well, there's a problem showing up here because if I wanted to implement braiding for a standard topological superconductor, I needed to keep my Majorana zero modes far apart from each other at all times. And this isn't possible in the case of a TRITOPS wire because the Majorana-Kramer's pair will always be in the same spatial location. So in order to understand what happens with braiding, we now need to consider what happens if we include local time reversal symmetric perturbations. So what I'm saying here is you could imagine that I have some gapped energy states, some Andreev bound states here, let's say at energy epsilon. Time reversal symmetry prevents the Majorana-Kramer's pair from hybridizing with each other directly, but it doesn't prevent them from hybridizing with some adjacent states. So in particular, there are terms I can write down that are symmetric under time reversal symmetry. And so I have essentially two different types of couplings between my Majorana-Kramer's pair and some adjacent bulk states. I'll still have exact zero modes at this end of the system, but now instead of corresponding to this dark purple dot, they'll correspond to some superposition of the dark purple and these two pale gray dots. So more explicitly, what I mean is that your Majorana-Kramer's pair definition will depend on the coupling determined by these time reversal symmetric perturbations. Now, if I assume some form of this coupling, so I have some coupling amplitude beta, and then at some angle that corresponds how this gamma 1 up corresponds to the lower Andreev bound state versus gamma 1 down to the lower Andreev bound state. And if this alpha winds in time, then what can happen is you can implement a unitary rotation that will slowly rotate your Majorana-Kramer's pair definitions into each other. So this was worked out in these two papers from 2014 and 2016. If you're interested in the details, they derive what they call it a local mixing angle should be. But essentially, it's your Majorana-Kramer's pair on this left end of the wire depend on these couplings, And if this alpha follows a closed cycle over time, you can derive some local mixing angle, and essentially this implements some unitary rotation on the system. And the important thing to notice is that this unitary rotation looks very similar to our braiding operator, except for whereas for the case of a topological superconductor, we had this quantized braiding phase of pi/4. Now we have some angle theta. And in this case, this theta is given by minus 2 pi n, the ratio of beta squared over epsilon squared. So here I'm assuming alpha winds by 2 pi n, and then beta and epsilon are just the ratio of coupling between your Majorana-Kramers pair and some bulk energy states over the energy gap. So what I want to emphasize here is that this angle theta is non-universal. It depends on this local physics given by beta over epsilon. So the end statement here is that you do not have protected braiding for a TRITOPS wire. Rather, these time-dependent local symmetric perturbations result in a non-universal rotation of the state, even if you're not actively trying to braid. So this means braiding is not protected for a TRITOPS wire, and so unless you're doing something very clever, a TRITOPS wire in general is not a good candidate system for a topological qubit. So these are the main differences I want to highlight about a TRITOPS wire compared to a topological superconductor. We now have a pair of Majorana zero modes at either end. We have our Majorana-Kramers pair. We still have a protected ground state degeneracy, but we do not have protected braiding.
I'm sorry, can I ask a question? So you talked about the physical realization of just the usual Majorana wire, but what would be a physical realization of these TRITOPS?
There are a couple of different proposals. You could have a quantum spin Hall system with a superconductor proximatizing one of the edges. That's one proposal. And I'll talk at the very end briefly about an experiment looking at the Josephson effect for that type of system. There are also proposals of essentially having some semiconducting two-dimensional system, having two superconductors on either side with a narrow junction, so you're proximatizing the junction, and then having a fine-tuned phase difference across the junction. That's kind of a conceptually simple example, but might be hard to actually implement in experiments because it requires fine-tuning of the phase difference across the junction. For this talk, I'm mostly just thinking of a cartoon type of picture where I just have two copies of a Kitaev chain. But there are also implications, which I'll mention at the end, for how you could have two of your standard Majorana nanowires, and they could act like a TRITOPS wire.
I see. So even though each of them breaks time-reversal symmetry because you have a magnetic field, you could still not hybridize the two end Majoranas.
Yeah, so actually in that case, what I'm thinking is if you think about, so they break time reversal symmetry in the standard way, so you don't have a t squared equals -1 symmetry, but the microscopic Hamiltonian has a t squared equals +1 symmetry, meaning it's symmetric under complex conjugation. And in that case, it turns out that you can get very similar physics to what you have for the TRITOPS case. And you can make it so that you still don't have hybridization between the Majorana zero modes at either end or at the same end of the wires.
Okay, thank you.
Yeah. Okay, so now we'll move into the meat of the talk, which is asking about the Josephson effect for a TRITOPS junction. So before we jump into that, we'll quickly review Josephson effect for conventional superconductors and for topological superconductors. So Josephson junction is a cartoon picture is just I have two superconductors. They're separated by some weak link, and I can have Cooper pairs tunneling across the junction, creating some supercurrent. And in general, this current will depend on the phase difference across the junction. If I have a conventional superconductor, I have a unique ground state for my system. So I'll have a unique subgap state of the junction. And it turns out that the current across the junction is related to the energy of the junction by a derivative with respect to this phase difference across the junction. So this is a relation we'll use a lot. I of phi equals dE of phi d phi. And so in this case, I would expect that if I'm in the ground state of my superconductor and I change phi adiabatically, then I should stay in the ground state at all times. And so I'll actually have some robust adiabatic cycle where the system returns to itself after 2 pi evolution of the phase. So this is the conventional Josephson effect, which essentially is saying there's a 2 pi periodic current phase relation and that this is a robust adiabatic cycle. Of course, if you have any other noise processes that connect your ground state to excited states, then this could change what you would see for an actual adiabatic cycle, but in this ideal case, you would have a robust adiabatic cycle. If instead of conventional superconductors, I have topological superconductors at my junction, then the Majorana zero modes at the junction can mediate single particle tunneling. So in particular, I could describe the electron hopping across the junction in terms of my 2 Majorana operators. And if I do a low energy projection, then the left electron essentially is just projected onto the Majorana zero mode at the left side of the junction, and the right one is projected onto the opposite Majorana zero mode. And what you'll notice here is that this single particle tunneling term is now going to depend on phi over 2. In particular, I'll get a cosine phi over 2 dependence. And so I can plot the energy spectrum of the junction against the phase difference. Because I have this pair of Majorana zero modes, I should have 2 subgap states corresponding to even parity and odd parity. And throughout this talk, I'll denote even parity with a solid line, odd parity with a dashed line. And these 2 states will cross at phi equals pi. And in particular, the ground state evolves into the excited state after a 2 pi evolution. So now if I do this relation of looking at the current by taking a derivative with respect to the energy, I would expect to see a 4 pi periodic current phase relation, because after a 2 pi evolution, I'll go from being in this ground state to being in this other subgap state. I'll mention that even though you might think we can't strictly rely on the adiabatic theorem because I have a crossing here, because these 2 states correspond to even and odd fermion parity, they can't couple to each other unless I include some additional processes. And so that's the meaning of having a robust adiabatic cycle for the fractional Josephson effect for topological superconductors. Okay, so then what happens for a TRITOPS junction? Again, I have a Majorana-Kramers pair at either end of the junction. So now I have single particle tunneling, but time reversal symmetry means I'll always have 2 such terms that are related to each other by time reversal symmetry. So this is just one example of the type of term that I could have. And then a similar low energy projection suggests that the energy spectrum should be, again, 4 pi periodic, where the ground state at phi equals 0 evolves to a different state at phi equals 2 pi. Now, because I have 4 Majorana zero modes, I'll have 4 subgap states, 2 of each parity. So now I'm going to focus just on the even parity states, so these solid lines. And the claim is that these are related by time reversal symmetry at multiples of phi equals pi. So the reason for that is for a TRITOPS wire, each of the wires satisfies its own individual time reversal symmetry. And then if I have a Josephson junction where there's some phase difference across the junction, I only satisfy a global time reversal symmetry at multiples of pi when the phase difference takes a multiple of pi. So I'm going to call these the time-reversal-invariant points. So in particular, this enforces the even parity states to be degenerate at phi equals pi, or at multiples of odd integer values of pi, and the odd parity states to be degenerate at even multiples of pi. Okay, so again, from looking at this picture, at the level of analysis where we just say the current is related to the energy by a derivative, you might think that this should have a 4 pi periodic current phase relation or a fractional Josephson effect again. But it's worth actually considering in more detail what happens at this crossing since I now have degeneracy between states of the same fermion parity. So to look at this, you might be tempted to just apply everyone's favorite 2-level Hamiltonian, the Landau-Zener Hamiltonian, to say near the junction, I can just linearize this cosine. So I essentially have CT sigma z plus A sigma x, where in this case, CT is just determined by how fast you're sweeping through the junction, and A would be if I had some gap at the junction. And this is a problem that we can solve exactly where the transition probability from the ground state to the excited state is given by this formula. And in this case, because we have a symmetry protected degeneracy at phi equals pi, A goes to 0, so you would expect this transition probability to go to 1. So this quick naive analysis would tell us that we should sweep through this crossing at phi equals pi and that you should have a 4 pi periodic effect. And so for this reason, people have proposed that there is a 4 pi periodic fractional Josephson effect for TRITOPS junctions. This is actually something that people have tried to see in experiments, and we'll talk about that a little more later. However, this isn't quite valid. This type of analysis isn't valid in this case because we actually have time-dependent states. And so what we want to do is look more carefully at the effect of time-dependent local symmetric perturbations. So in particular, look at the same type of perturbations that ruined braiding for a TRITOPS wire and see what effects they have for a TRITOPS Josephson junction. Okay, so this slide's a little busy, but we'll just walk through it. I again have my TRITOPS Josephson junction, and now I'm considering what happens if I have coupling to some nearby bulk states. So this is the same as what we looked at for braiding for a single TRITOPS wire. On the top here, I'm showing a minimal model of a Josephson junction Hamiltonian that's symmetric, time reversal symmetric. This is not the only such term you could write down. And then in particular, I'm assuming that I have two types of perturbations. And if I think back to the Kitaev model, this H mu term, for instance, given by this top line, just looks like a chemical potential type term in the Kitaev chain, whereas this H delta type term given here corresponds to, for instance, an S-wave pairing type term. So these are pretty natural perturbations to consider. And what I'm supposing is that the magnitude of these different types of couplings winds in time in some way, and that alpha winds by an integer multiple of 2 pi. So my full Hamiltonian is just going to have my Josephson junction Hamiltonian, the Hamiltonian describing these bulk states, and then the coupling between the Kramer's pair and the bulk states. What I could suppose is that I initialize the system in a superposition of my two subgap states of the same fermion parity, which I'm calling psi1 and psi2. Now, provided everything is adiabatic on the scale of the energy separation to my excited states, I can assume that the system remains in this ground state subspace at all times. And in this case, I'm interested in how these time-dependent coefficients V1 and V2 evolve in time, and that will be according to some effective Hamiltonian. And it turns out that this effective Hamiltonian takes this form, where we have, again, this cosine phi over 2 dependence that's set by the Josephson junction Hamiltonian. But now we'll also have some term that couples my two states that are related by time reversal symmetry. So in particular, I wrote it down in terms of this theta dot term. This is really the same type of expression that we saw in the case of braiding for a TRITOPS wire. So in particular, alpha is parametrizing the ratio between these two different types of couplings I have, and beta over epsilon is just the ratio of the magnitude of coupling between the states over the energy gap. So the important takeaway here is that we have some effective Hamiltonian that couples my junction eigenstates. And this is really showing up because I have time dependence in my states themselves. So now if I plot the, if I remind us of the energy spectrum of the junction against the phase difference phi, I can first think of kind of a proof of concept type picture of this system where I assume I have some control over this theta dot term and that it's 0 at all times except for at this time reversal invariant point labeled 2 here.
I'm sorry, can I ask a naive question? What is this theta again?
So this theta is this local mixing term. And
between the
okay, it's not so easy for me to change slides here. Okay. So if I go back to here,
yes,
to this picture, what it's saying is that if I ignore the junction for a second and I just have a single TRITOPS wire, then the type of perturbations that I've written down here, H mu and H delta, will rotate gamma L up and gamma L down into each other over time, according to some angle theta. And then it's not obvious from what I've said here, but for this particular type of perturbations that I've written down, this theta is essentially set by the rate at which alpha is winding in time over the ratio of beta over epsilon. And so the important thing here is just that they will rotate into each other over time according to some non-universal angle that depends on beta over epsilon, but only if these perturbations are time dependent. So that alpha of t is winding in time.
So that where does the time dependence of the perturbation come from? Is some kind of noise or?
Yeah. So the assumption here is that you'll generically have some type of noise. For instance, some type of S-wave pairing between your low energy states and some nearby bulk states, as well as some chemical potential type pairing. And so the idea is that this is governed by non-universal physics. And right now we're just taking a contrived toy model of what could happen for that noise.
Okay. Mm-hmm.
Okay. So theta is that mixing angle, and this is just describing some rate at which the two states are being rotated into each other. And so the statement here is that this mixing angle, the change in time of that mixing angle, is effectively coupling my junction eigenstates. So in particular, even though there is an exact ground state degeneracy here, and this is protected by your time reversal symmetry, because your states are time dependent, if you actually just look at the coefficient of your exact ground states and how they evolve in time, they'll evolve according to some effective Hamiltonian that takes this form. Okay, so now we're taking a simple model where we pretend that theta dot is not set by noise, but instead that we have some control over when theta dot is turned on or turned off. And we're first going to take a contrived example where it's only non-zero at the point where my states are degenerate. So this is just a proof of concept picture. What's happening here is that if I initialize in the ground state at phi equals 0, then and I evolve to 0.2, I'm just going to be evolving according to a sigma z Hamiltonian. So I'll just stay in this state until I reach 0.2. Now I'll turn on theta dot for some amount of time, and I'll just pause at this point. So in this case, I'm just evolving according to sigma y. So I'll just undergo some Rabi oscillations. And depending how long I pause at this point, and then turn off theta dot and move away from it, when I get back to phi equal to 2 pi, I'll be in some superposition of these two states just set by the Rabi oscillations at the degenerate point. So this is one sense in which you do not have a robust adiabatic cycle here, because if I had a robust adiabatic cycle, it wouldn't matter how long I paused at this phi equals pi point. I would always end up with probability 1 of being in this top branch. But now instead, I'll have some probability sine squared theta over 2 set by non-universal physics of being in the top branch. So, okay, so this is a contrived example of why you don't have a robust adiabatic Josephson effect for a TRITOPS junction. A slightly more, okay, so in general, this would correspond to some aperiodic current phase relation. So instead, we could ask what happens if we look at a slightly more realistic example where phi evolves linearly in time. So I can imagine I have a voltage biased Josephson junction. So phi dot is constant. And then now I imagine that theta dot is just turned on in the vicinity of this time reversal invariant point. And then I could look at how the transition probability from the ground state to the excited state depends on the smoothness with which theta dot is turned on. And what you can see is that if theta dot is turned on very abruptly, I'll plateau to some transition probability, which is just set by this local mixing angle. But then if theta dot is turned on and off more smoothly, I'll actually evolve adiabatically according to H effective, which means the transition probability will go to 0. And so with probability 1, I'll end up in the exact ground state at phi equals 2 pi. And that would correspond to a 2 pi periodic current phase relation or conventional Josephson effect. So what this is saying is that for this slightly more realistic but still somewhat contrived example, I will generally have an aperiodic current phase relation, but I could access a conventional Josephson effect regime. And this would really just depend on the noise physics. A different special case you could look at is that both phi dot is constant and theta dot is constant. And in this case, I could linearize H effective near the time reversal invariant point and just end up with my Landau-Zener Hamiltonian again. And then I'll have a regime where I could have a 2π periodic current phase relation, which essentially means I evolve slowly on the time scale of local mixing so that the states have a lot of time to mix near the time reversal invariant point. I could have these two be comparable, in which I'll have aperiodicity, or I could evolve sufficiently quickly that local mixing doesn't have time to have an effect before I've moved away from the degenerate point. And in this case, I will be able to access a 4π periodic regime. So if I combine this with the previous case, we see that depending on how fast you sweep the phase difference, phi dot, compared to this theta dot, which is just set by noise, so set by some local physics, you could see a 4π periodic effect, you could see an aperiodic effect, or you could see a 2π periodic effect. And in reality, whichever you see is giving you some information about the noise of these of this particular type of time reversal symmetric perturbations that is happening.
Can I ask a little question? So if you had some noise, I would suppose this theta dot would average to 0, maybe some kind of noise, and then it would be like kind of higher order, or
Yeah, so what you might imagine is that theta dot is averaging to 0, but it could be doing that by either having this alpha parameter winding very quickly, so picking up a lot of cycles, or winding very slowly. Or sorry, I said that wrong. Winding very quickly, so you pick up a lot of cycles, or kind of fluctuating back and forth so that you don't actually wind in any way. In the latter case, you would not expect local mixing to have any effect, and so you should have a 4π periodic Josephson effect. But in the former case, where maybe there's some type of fluctuation that's just kind of constantly winding in time, in that case, you would expect to have aperiodicity showing up.
Okay.
But it wouldn't necessarily be the same for every cycle you look at. It might be that sometimes you see some aperiodicity, occasionally you see 2π periodicity, and it's all just set by local physics. But the important takeaway here is, just as braiding is not protected in any way for a TRITOPS Josephson junction, you don't have a robust adiabatic Josephson cycle, even though you do have a protected degeneracy. That doesn't mean that it wouldn't be possible potentially to pull out a fractional Josephson signature from an experiment, but it means that it's not protected in the same ways that a topological Josephson effect is protected. Okay, so this is a quick summary of what we've talked about so far. So we first looked at Majorana zero modes for topological superconductors. We looked at how time reversal symmetry gives you a Majorana-Kramers pair at either end, and that you have non-universal braiding despite having a protected ground state degeneracy. And now what we're seeing for a fractional Josephson effect for TRITOPS systems is that generically you'll have an aperiodic current phase relation. This is sensitive to the local physics. So even though you have this symmetry protected ground state degeneracy, it does not imply a robust adiabatic cycle. So now I'd like to mention briefly two implications of this result. And the first is for experiments that I briefly mentioned before on proximatized quantum spin Hall edges. So first, this is of course a theory paper kind of outlining the setup where you have some quantum spin Hall system, and then you have superconductors at either end, and the Josephson junction is mediated by the quantum spin Hall edges. Now in the theory paper, if you look in the non-interacting limit at the subgap states for this system, so this is a slightly different type of TRITOPS than what I was considering. You have these subgap states that can, in general, connect to the continuum, and you have this fourfold degeneracy, including between states of the same fermion parity. So again, solid versus dashed lines correspond to states of different fermion parity. However, interactions will open up a gap at this avoided crossing. So this is what panel D is showing. And in this case, you would actually predict to have an 8 pi periodic Josephson effect. And so a way to see this is that if you initialize the system at phi equals 0 in this state, then after evolving by 2 pi, you should end up here because this is a crossing between different parity states. Then you'll come out on this side, you'll evolve to here, evolve to here, evolve back down to here, and then return to your initial state. So you have to undergo 4 of these cycles, which is why you get an 8 periodic Josephson effect to return to your initial state. So this was the theory proposal, and then some recent experiments attempted to see this 8 pi periodic Josephson effect in mercury telluride-based Josephson junctions. And so in this first panel, they've tuned the system into a trivial regime just to check that everything's working. They're looking at an AC Josephson effect, and they see Josephson radiation along this line corresponding to the Josephson frequency, and this corresponds to a 2 pi periodic effect. So they're saying everything's working when the system's tuned into the trivial regime. They then look at 2 different cases of whether this junction corresponds to a 3D topological insulator or a 2D topological insulator. And in either of these cases, the theory predicts an 8 pi periodic effect, and instead what they see is some signatures at conventional Josephson effect, for instance, along this line here, and of a 4 pi periodic effect along this line here, corresponding to frequency fj over 2. But they don't see any signatures corresponding to an 8 pi periodic effect. And so there are various possible explanations for why they don't see any 8 pi periodicity. But one potential is that the same type of local mixing that we were looking at for a different type of TRITOPS wire could be occurring at these multiples of 2 pi, where you have states of the same fermion parity becoming degenerate. And so again, you could be in a regime where local mixing is, instead of taking you from this state up to this one, is transferring you from this one down to this one. Okay, so here local mixing could be a potential complicating factor of the analysis of this type of experiment. And then the second outlook I wanted to mention is that you can actually apply a similar analysis to multi-wire topological Josephson junctions. So this is just a reminder, if I had a single topological superconductor on either side, what I would expect the spectrum to look like. And in this case, I'd expect there to be a robust 4 pi periodic Josephson effect. If I have a multi-wire junction, so here I'm imagining that I have M topological superconductors on either side, and then I'm proximatizing them all by the same trivial superconductor, just so that they are all fixed to have the same superconducting phase on either side of the junction. Then, as I briefly mentioned before, it turns out the microscopic Hamiltonian for this type of system satisfies a t² equals +1 symmetry. It's kind of an accidental symmetry. We don't know the degree to which it's there or not in experiment. So this analysis is assuming first that this t² equals +1 symmetry is there, and then we'll talk in a little bit about what would happen if it weren't. In this case, you would expect, if I look at a non-interacting limit, for instance, for 3 wires, that I'd have an energy versus phase spectrum that looks like this, where I have a bunch of degeneracy here, and then a similar analysis would apply where you could have local mixing, so generically an aperiodic effect. But then in the presence of interactions, it actually moves some of these crossings off of this time reversal symmetric point, and then you could, in general, have avoided crossings opening up between them. So in this case, you'll end up having a 4 pi periodic effect. For instance, if I focus on this state, if I evolve by 2 pi, I'll end up over here, come out on the other side over here, and end up back down here. So just to summarize, you can look at what happens with different numbers of wires on either side of the junction. The non-interacting case, as soon as you have more than one wire, you can have local mixing corresponding to an aperiodic effect. But in the case of interactions, the 2-wire case will look very similar to the TRITOPS Josephson junction we just looked at. So you could have a 2 pi, 4 pi, or aperiodic regime. If you have an odd number of wires on either side, you'll end up with a 4 pi periodic effect. And then for 4 wires, you'll trivialize the system and just end up with a conventional Josephson effect, which means all crossings will be opened up. You won't have any degenerate points. So the reason that this is interesting is that this can actually be a way of probing the Z to Z8 classification of interacting fermionic topological phases. So there's a famous result by Kitaev and Fidkowski where they look at how you can combine different topological superconductors, assuming a time reversal symmetry, and at what point you return to a trivial system. And they see that the phase with 1 wire, 2 wires, 3 wires, up through 7 wires are all distinct. But once you add an 8th wire, it is equivalent to the phase with 0 wires, 0 topological wires. This is actually a way of probing that out of systems that we believe we can realize experimentally by looking at the periodicity of the fractional Josephson effect. So I'm happy to talk more about that if people are interested. But this brings me to the end of the talk. I'm happy to answer any more questions, and I'll just put this summary up in case anyone would like a reminder.
Thank you very much, Christina. So are there any questions from the audience? Okay, I see no questions. Maybe I can ask. So you said that to have this kind of 8-pi periodic Josephson effect, you need to have like either a quantum spin Hall edge or otherwise pairs of wires. Okay. Actually, there is one recent work, one work that I was involved in some time ago, and we showed that in principle you could have this 8-pi periodic Josephson effect even in a single key-type Josephson junction.
Oh, okay.
So that breaks time-reversal symmetry, but effectively, if you have a perfectly transparent junction, namely, like the junction is the transmission probability 1 across the weak link, then you get like an effective low energy time-reversal symmetry in the model. So you can pretty much map to the low energy effective model is similar to that of Young and Kane. Yeah.
I see. Okay, so in that case, it's a t² equals -1 time reversal sim.
Yeah.
And then how do you? So in their model, it's important that you have more than just 2 subgap states. Is that also the case for when you just have 2 Kitaev chains?
Yes, I think so. Yeah. So you need to have. Yeah, I don't recall now the details. This was published over a year ago, but so from what I remember, the effective model becomes very similar to this the 2014 paper of Zhang and Kane. Yeah, but even for just one single Kitaev Josephson junction. Yeah.
So then what I would expect is if in that system you still have degeneracy between states of the same fermion parity where it's now protected by this emergent time reversal symmetry, I would expect that you can make a similar argument of there being some local mixing terms that could couple the states, but I don't know how likely that type of noise would be to show up in that system. It might be not likely.
One of the problems for us was that these interactions, we did actually a calculation of this many variable bump structure, and I think in order to have this some reasonable chance of seeing this 8-pi periodic Josephson effect, you need to have fairly strong interactions. So what would happen, for example, in the plot that you're showing, if these interactions were very weak? If the gap was very weak, you would would probably not see the 8-pi effect. Because
it would put strict constraints on on the evolution not only of the phase but of any other local noise processes that might be introducing transitions between states.
Okay.
But this multi-wire junction setup is something that we actually hope should be able to be probed through experiments on a somewhat near-term scale. This is pretty similar to one of the proposals for how you'd build a Majorana-based qubit, where you have multi-topological wires that are connected by the same superconducting island. And so being able to probe whether or not you see this 4-pi, 2-pi, 4-pi, 2-pi type effect for changing the number of wires, if you were able to see that, then it would mean you'd have this t² equals +1 symmetry, which actually is detrimental for how you would propose to read out these types of qubits. But if instead you didn't see this kind of alternating type of periodicity, it might be an indication that time reversal symmetry breaking perturbations are strong in these wires, and that would be pretty favorable for the Majorana qubit readout proposals.
Okay.
So it's something that either result gives you a pretty interesting answer.
I see. Okay, let me check the chat if there's any. No, David's in the chat.
Yeah, okay. Yes,
yeah.
I'm a bit confused. I mean, is there, maybe I missed that, but I mean, the relation between the number of wires and the t-square symmetry, is it -1 for an even number and 1 for an odd number, or?
Oh no. In this case, we're assuming each individual topological superconductor wire satisfies a t² equals +1 symmetry.
Okay.
And so this is something I skimmed over, but one proposal of how you realize these types of wires is by proximatizing a semiconducting wire with a standard superconductor and then applying a magnetic field.
Yes.
And in that case, the microscopic Hamiltonian turns out to be real. So it's symmetric under complex conjugation. There's not some fundamental reason why that type of symmetry should be there, but no one's ever been able to measure, or as far as I know, no one's measured the degree to which it's broken.
Mm-hmm.
And so it turns out that readout proposals for this type of qubit rely on that symmetry being broken. And this could potentially be one type of experiment to either see that it's there or that it's broken.
Okay, thank you.
But without that type of protecting symmetry, you don't have this degeneracy, for instance, in the non-interacting case at phi equals pi.
Okay, so well, I guess if there are no further questions, so we can conclude. So thank you, Christina, for taking the time to share your results. And yeah, so good luck in your new move.
Thank you, and thank you all for listening.
Yes.
All right, stay
Pleasure.
well.
Thank you.
Bye-bye.
Bye.
Merci, Carl, pour l'organisation de ces changements de dernière minute.
Pas de problème, Yann, je vais arrêter l'enregistrement maintenant.
D'accord. Ouais.
Merci
Effectivement,
encore.
est-ce que cette présentation sont gardées quelque part ou...
Oui, certainement. On va les mettre sur notre chaîne, probablement sur notre chaîne YouTube bientôt, mais c'est en configuration en ce moment. Ouais.
OK, super. OK, merci beaucoup, Carl.
C'est bon. Bonne journée.
Bye.